Good day. Today I will talk about the Kakutani Neumann transformation. This is a transformation defined on the unit interval, and it was defined by Kakutani and Neumann in the 1940s. We will use this transformation also to illustrate a process called cutting and stacking that is a very useful process for defining transformations on the unit interval and also on the real line that have the property of being measure preserving and ergodic. So this process gives a large class of ergodic measure preserving transformations on the unit interval or the real line. So the Kakutani Neumann transformation is one of the first ones, and our definition will use the idea of cutting and stacking. This idea, this construction is inductive. So we start with a sequence of what we will call a sequence of columns, and this will define the transformation. So before starting our definition, we will illustrate what we mean by a column and a column map. And before we start with a column map, so we'll talk about a column. So a column Cn consists of a sequence of levels. We will use C or Cn, but maybe at the nth stage we will have a column Cn, so might as well denote it by Cn. Will consist of a sequence of levels, and we will denote our levels I sub n0, since we are at the nth stage. The next level is I sub n1, I sub n sub h sub n minus 1, where h sub n is going to be the height. H sub n is said to be the height of Cn. We'll write here, this is the height of Cn, the height of the column Cn. Okay. So a column is a sequence of levels of intervals. We will call this, we refer to them as levels or also as intervals. So this is intervals of the same length. Okay. So we have the idea of a column, a finite sequence of intervals of the same length of height height hn. Now, before defining the column map, we will note that given any two intervals, there's a unique orientation preserving translation between them. So I will illustrate this. Suppose you have any interval here, say from A to B, and an interval here from C to D. There's a unique map or a translation that sends this interval to the other one. So we'll send a point here x to a point here, and we will denote that point as T sub x, T of x. This T of x is a map that depends on the levels that are given. Okay? So this will just be a translation. One can define a map that sends A to C and B to D. One can write an explicit formula. Okay? So with this idea that any two levels have a unique orientation preserving translation between them, we can then define a column map. Given a column, we can define a column map. So let's look here at a column C. And let's suppose you have a column Cn. You have the bottom level here, which is I sub n0. The first subscript refers to the fact that this depends on the column n, Cn, and 0th refers to the level, 0th level. Then there is the next level here, I sub n1, up to the last level, which is I sub n, and the height here, this is h sub n minus 1, because this has hn many levels. Okay? So Note here now that giving any point anywhere in the column, say here, we know we have a map that we will call T sub n, T sub Cn, and there's a unique map that sends the point x to the point in the level above it. So here, in this case, I will draw the next level. Here's the next level, and T of x is a point in the next level. Okay? The interesting thing here, actually, one can already see that we can iterate this. There's a next. This is x. This is T of x, and this point would be T of x, which we call T2 of x. Okay? So points go up. To specify the map, all we need is to give a column that consists of levels, and giving a level, we know the point above that, where the point goes to the in the level above it. Okay. So what we have defined so far is the notion of a column, a sequence of levels, the height, and giving a column, there's a corresponding column map that we're denoting here by T sub Cn. The column map depends just on the column. The columns sometimes are called towers, and these are also called Rochlin towers or Rochlin columns. All right. Now what we're ready to define, our Kakutani Neumann transformation. And what we're going to do is define inductively a sequence of columns. We start with column C0, and in this particular case, C0 consists of just the unit interval 0, 1. Okay. And then what we have to do is we have to specify a process, an inductive process, to go from column Cn to column Cn plus 1. This process uses an idea that we call cutting and stacking, and we will illustrate this for a specific case of how to construct C1 from C0. Okay, first we will show how to obtain C1 from C0 using this idea, and then we will talk about the inductive case. Okay, so suppose we look here at C0, and C0 consists of the single level, which is the interval 0, 1. The height of C0 is h0, which is 1. So what we do is cut this in half. So what we're going to specify, you have some rule, and the rule for this particular case of the Kakutani polynomial transformation says you cut in half. So this you cut in half, and you, in this case, will cut in the interval at the point a half. Okay? So we cut in half, this is the point, and then we stack, and we say that we stack the right half on top of the left half. Okay? So here, so this is column C0. So to define column C1, we cut C0 in half, and then we put here the first interval 0 half, and then the interval a half 1 on top of it. Okay? So we did cutting and stacking. So we have a new column C1, and note here that we have already a partially defined map, which we know it sends this point to the point above it, and this would be T sub C1 at x, is the column map applied to a point, an arbitrary point, x in the interval 0 half. The column map is completely determined by the column, and in this particular case, since we know this is the interval that goes from 0 to half, and it should go to the interval to half 1, we know that this map has to be x plus a half. So we know, in this particular case, the formula for the column map. Okay? It will not be necessary. It's important to know if we wanted to, we can determine the formula in each case. But for a lot of the dynamical arguments that we will make later, the specific formula is not necessary. Will not be necessary. All right. So C1 has been obtained from C0, and it has been obtained for the process of cutting and stacking. And we already have here a column, and we can talk about its height, h1. This has height 2. All right. So now what we do is we're going to define the inductive step. So the inductive step assumes that suppose we're giving a column Cn of height hn. So here's the levels, and this is Cn, and has hn. So Cn consists of hn levels. In this particular case, one can figure out what Hn is, and we will see in a moment. So Cn consists of Hn levels, and the important thing, all are of the same length. Now, how do we obtain Cn plus 1? We cut each level in half. So we cut each level in half and stack the top, we stack the right on top of the left. So here we will see C in Cn plus 1. We'll see that it starts, we can see it starts here with this half level, starts there, goes up to here. That's that half, and I'm making the height a little bit lower in order to fit in this area. And then we stack this part on top. So here it is, there. Okay. So here we had Hn levels. So here we have Hn many levels. Here we have Hn many levels. So the height of Hn plus 1 is 2Hn, from which we can deduce that Hn has a formula equal to 2 to the n. One can figure that out. All right. Now, to illustrate this, sometimes what we're going to do is use, to signify what's happening here, is we will draw an arrow that shows where this top left is going. Let's make a few remarks here. So we have shown the inductive step, and therefore we have defined now a sequence of columns Cn for each natural number n. Okay? Each column consists of Hn levels, or intervals, all of the same length. Okay. Note that each column map is defined on every level except the top. Now in Cn, for example, the column map T sub Cn is not defined here. But what Cn plus 1 does is extends the definition. Suddenly Cn plus 1 is going to be defined on the top left of Cn. So we know top left of Cn is going here, and that's here. So we gain definitions each time on the top left. If we look at that argument in more detail, we note that this means that we have defined a transformation on the whole unit interval. Since we are choosing the interval left closed, right open, if you take any x there, x will be to the left of 1, and one can observe that such x will be in some column where x is at a level that is not the top level. You can always find a column where x is not the top level, and therefore you will know what t of x is. So this sequence of column maps define, so now we have this defines, we write, defines t. Defines a map t from the unit interval 0, 1 to itself. So we have, and there's one more property that I want to mention here, and before we finish this part of the presentation. We'll observe that for any column, as we see here, if you have any set, a measurable set A, is sent to a, T of A will be another measurable set of the same length, because T of A is nothing but a translation. T on each level is a translation. Okay. So to review what we have done is we have illustrated the process, an inductive process called cutting and stacking, and we have used that to define a transformation on the unit interval, and we have observed this transformation is defined on every point on the unit interval, and it is a measure preserving transformation. We will talk about the idea of measure preserving in more detail in the second part of the presentation. So this ends our first part with the definition of the Kakutani Neumann transformation on the unit interval.